Today I will be talking to you about the Australian Source Rock and Fluid Atlas, built on historical data archives held in the ORChem database and delivered through Geoscience Australia's Data Discovery portal. This presentation is going to take you on a geoenergy data journey from the drilling of the first wells in Australia to the vast datasets collected in the Exploring for the Future program. I would like to acknowledge my co-authors who helped populate and build the database and deliver the database in the Atlas. I would also like to extend my thanks to other team members, starting with the repository where the rocks and national oil and gas collection are stored, to our laboratory technicians who analyse the samples, and the MEG Information Services and Geological Indexing for providing digital pathways for getting our science to users, as presented by Mark Webster. And finally, the Data and Data Digital Services team who maintain and build the portal. The energy section is delivering data of enduring value to the nation in support of the government's energy transition to net zero. Today I'm going to be talking about the laboratory analysis and data delivery of sample-based data from the ORChem database, with a focus on source rocks and their generated fluids collected from sedimentary basins. These samples originate from petroleum stratigraphic wells drilled across the Australian continent that have organic geochemistry, petrology and stable isotope data. Importantly, I will demonstrate how pre-competitive data acquired through the Exploring for the Future program and legacy datasets can be repurposed to help solve today's challenges. The Geoscience Australia Data Discovery portal is key for discovery and accessibility of spatially located data that can be downloaded as maps and digital data files in the Source Rock and Fluid Atlas persona. The portal is used widely by the Minerals, Energy and Groundwater Division to deliver data. My talk starts with an introduction to what is the Source Rock and Fluid Atlas and how it is accessed. I will show you where the data comes from, why we collect it and who benefits. And then I will a description of the ORChem data tables and end with the conclusions. The Source Rock and Fluid Atlas is an online digital atlas of organic geochemistry, organic petrology and stable isotope data for samples from sedimentary basins with a focus on fine-grained sedimentary rocks, including mudstones and carbonates. Organic rich rocks which have the potential to generate hydrocarbons are called source rocks. If there are no source rocks within a basin, then there is no oil or wet gas. The pores in these rocks contain fluids, either natural gas, crude oil, or water. While most wells do not encounter oil and gas, every well recovers rocks and can be analysed in future studies. The ORChem geochemical database contains the physical and chemical properties of earth materials, molecular composition of organic compounds, and the stable isotopes and elements of inorganic and organic compounds. The ORChem database contains elements, compounds and isotopes of 5 non-metal elements: hydrogen, carbon, nitrogen, oxygen and sulfur, as well as the noble gases helium, neon, argon, krypton and xenon. The chemistry of these elements gets complicated very quickly because they can form many compounds, including hundreds of different hydrocarbons, all with isomers, and they all have several stable carbon isotopes. Stable isotopes of carbon and oxygen are also captured for carbonates as well as organic matter. So how do you access the portal and the atlas? From the portal address shown here, go to the left-hand side of the menu and click Layers icon. When you click on this layer group, over 60 layers of many subjects appear in alphabetical order. Hence the geochemistry and the organic geochemistry layers are some way down. So alternatively, there is a quicker way, and that is to use the Source Rock and Atlas persona, which can be found on the right-hand side of the top menu by clicking on the persona icon. Scroll down and select the Source Rock and Fluids Atlas tab, or use the web link as shown here. The map now changes, and when you click on the About icon, you get information about the atlas. And when you click on the Layers icon, you now get a limited number of layers, including boreholes, geochemistry, geology, infrastructure and tenements. There's also another layer called the geological storage of carbon dioxide, which is related. When you click on the geochemistry layer, you can see all of the different web services for organic geochemistry. If you go down and select the natural gas composition layer and choose Add to Map, for the hydrogen layer, you can now see the location of the gas samples with the hydrogen data. You can change the legend by clicking on the legend, and the style will then show you the concentration of the hydrogen in mole percent. Now you can click on Information, which gives you more information about that layer. To download the natural hydrogen gas data, click on the download icon. Select the CSV file, and this dataset will now be saved as tabular format. There is also the option to save data in JSON format to read from a web application. Alternatively, you can also save the data in KML or shapefile formats used to display geographic features. The great achievement of the portal is that once you know how to access one layer and download the data, this process is the same for all other data layers. The hydrogen CSV file is downloaded onto your Downloads folder and can be opened up in Excel. I suggest that you sort the columns by geological province, borehole name, and sample top depth. All of the data in the tables is displayed in the same order, starting with the borehole information. This is then followed by the sample number, sample depth, top depth, base depth, and then we move on and you get information on the geological province and the stratigraphic unit information. Then you scroll over further on your Excel spreadsheet, and in this case the geochemistry data is shown here, with the emphasis being on the hydrogen molecular data shown in the map. This data in Excel has been filtered, but you can also do that in the portal. The molecular data you see in the spreadsheet was obtained using a gas chromatograph, which separates the individual compounds of natural gases. In the bottom trace, you can see where helium and hydrogen is separated. Now I would like to explain where the data comes from and why and who needs it, which is steeped in the history of exploration and legislation and the evolution of laboratory analysis and data discovery technology. There is legislation that must be followed for the drilling of wells on the Australian continent, and there are governance and data discovery guidelines concerning all derived information. There are efficiency gains from entering and quality controlling the data once into an expertly managed database, i.e. have a single point of truth. The data can be used an infinite number of times by many stakeholders for many different reasons. We need large data sets for integration and multi-purpose use, particularly for advanced analytics, machine learning, and for artificial intelligence training data sets. These technologies help to develop predictive capabilities and de-risk the discovery of new resources. And finally, we have a laboratory at Geoscience Australia for 56 years, providing pre-competitive data since the BMR to AXO and now to the new Geoscience Australia laboratory. Over 15,000 petroleum wells and 8,900 stratigraphic wells have been drilled in the Australian continent, as visualised by this clip showing the location of wells drilled each decade, starting before 1910 and continuing to the present day. The most recent drills include the Exploring for the Future Barnacardy-1 well drilled in the Canning Basin and the NDI Carrara-1 well drilled in the Carrara Basin. We have loaded geochemistry data from over 6,500 wells, which comprises some 138,000 samples and over 1 million rows of data. Not all wells have sample data, but there is still a lot of data to be captured. Hence, our data tables are not yet complete, but they are live, data is being added, and the web services update overnight. The Oracle and pyrolysis and gas data tables have been running since 1998, with the earliest total organic carbon values being recorded in Majura 1 in 1902. And the earliest gas composition is from Robe 1, drilled in 1915. Interestingly, some of these early wells record high hydrogen values, as explored in Chris Boren's Natural Hydrogen talk. Geoscience Australia's Strategy 2028 states that the geoscientific data and physical collections have enduring value. Our Data and Digital Strategy 2028 goes on to say the government, industry and community expect Geoscience Australia's data and products to be easy to find, access and consume. And I stress the word consume. We have a product catalogue, ECAT, which provides our records and data releases. The output for these are in Word, PDF, Excel or PowerPoint documents. They're easily read by humans, but not by machines. As Mark Webster went on to explain, the data delivery portal provides the technology to consume data, downloaded tabulated data and spatially located geographic data files. So who benefits? Geoscience is for all Australians. Although the Source Rock and Fluid Atlas contains highly technical data and is primarily used by geoscientists in research organisations, government and companies, everyone should be able to find out where Australia's resources are located and what information is available for a borehole drilled anywhere on country. So the last section of my talk lists the data tables available in the Atlas and gives some examples of how we are using the data. The Exploring for the Future project has enabled the existing data tables to be extended to build new ones. We now have web services covering the physical and chemical compositions of sedimentary rocks, crude oils and natural gas. We have 3 gas data tables that contain molecular and carbon and hydrogen isotopic composition, as well as the stable isotopes of the noble gases. A new web service contains the molecular and isotopic compositions of soil gas, where baseline studies are being conducted in regional New South Wales near Tumut, looking at the distribution of naturally occurring hydrogen helium. The results from this study are presented in Chris Borum's Natural Hydrogen talk, and the data released in this new report will be uploaded into the database. We have 8 tables that contain screening data for rocks, including pyrolysis, pyrolysis gas chromatography, and transmitted and reflected light microscopy, to look at the organic matter in the rocks. The combined pyrolysis and vitrinite reflectance measurements have been combined into a new table, where these 2 types of analyses are used to screen source rocks for their organic matter content and level of thermal maturity. These data have been collected for over 30 years, and we now have over 25,000 records entered. These data are used for import into basin models, such as that used in the Adder Vale Basin in the Exploring for the Future project. In the central part of the basin is the Gilmore gas well, where the pyrolysis parameters, total organic carbon, S1, S2, hydrogen index, and vitrinite reflectance are plotted down with depth. These parameters are used to constrain the organic richness and thermal maturity used in the models shown here. We have 5 tables that contain bulk, molecular and isotopic data for oils, source rocks and fluid inclusions. There is a separate table with the carbon and oxygen isotopes for carbonates. And we have a table where organic and inorganic geochemistry have been combined. So for my last 2 case studies, I'm going to show you the API gravity property from the oil and rock table, followed by an example using the combined organic and inorganic geochemistry. As explained by Claire Patterson's talk, enhanced oil recovery projects inject carbon dioxide into depleted reservoirs to recover the last of the oil resource, and information used in these projects are stored in ORChem. Firstly, the natural gas composition table holds the concentration of carbon dioxide in petroleum wells that can be overlaid on basins that may have the potential for enhanced oil recovery projects. Secondly, the density of the API gravity of the oil that is to be recovered typically needs to be greater than 27 degrees. The colours on the legend attempt to match the colours of the oil. The collection of oils from Northern Australia is ordered by the API gravity, which is higher on the left and lower to the right. These are condensates and light crude oils from fields that may be suitable for enhanced oil recovery projects. Another new web service combines the organic and inorganic databases together, which is particularly useful in investigating the redox conditions required for the precipitation of minerals. This is an example from the Tullabuk Formation in Queensland, where you can see that the concentration of uranium increases with the total organic carbon content of the rock. So in conclusion, this is only the beginning. The Exploring for the Future program has enabled the addition of data tables to hold most organic geochemical datasets and develop the Source Rock Fluid Atlas persona for data release in the Data Discovery portal. Importantly, I have demonstrated how these new Exploring for the Future and legacy datasets can be repurposed to help solve today's challenges, particularly in the discovery of natural hydrogen resources, the sequestration and utilisation of carbon dioxide, and the mineral resources coupled with the organic matter in source rocks. The task now is to enter more data, integrate these into regional mapping projects, and give more talks about how to use these datasets. Thank you.